All right, in this video, we are going to talk about the graph of the cosecant function. If you haven't already watched the video for the secant function, then I recommend that you go back and watch that because the analysis here is going to be, very similar to that. So there's, I'll go into it in more depth in the secant video. So definitely watch that one before you watch this one. Okay, so as in that video, if you want to graph the cosecant function, then my recommendation is to use the sine as a guide. Once you know what the sine function looks like, then it's really not hard to figure out what the cosecant function looks like. All right, and so what I'm going to do is here I've graphed some points that are on the sine function, sort of that fundamental period from 0 to 2 pi. And just so you can see, they're on the sine function themselves. And just like I did in the previous video about secant, what you can do is go through and figure out where all of these points are going to be on the cosecant. So you can see they're all in the sine. So I'm going to turn these cosecant points on. Okay. And you can see, right, for each one of these points on the sine, well, most of them anyway, then we are going to get a corresponding point on the cosecant, just like we did in the previous video, where we just took the reciprocal of the y-coordinate. So for instance, right here at, let me turn this one off. For instance, this one here at pi over 6, right, the sine of pi over 6 is 0.5. Well, that means since cosecant's 1 over the sine, that means that for the cosecant, you're going to have 1 over a half, which comes out to be 2, right? And so that's how you generate these points. If you know the points that are on the sine, which we've already talked about, you can easily generate these points on the cosecant. Now, there's a little problem right here on these points, for instance, 0, 0, right? Because the sine is 0, right? That means that the cosecant will be undefined, right? Because the cosecant will be 1 over 0, that's undefined. So on those points, right, where the sine is 0, for instance, at 0, pi, and 2 pi, right, you're going to have an asymptote there. Right, remember that is a line that the graph gets closer and closer to. And let's see, make those all the same color, and we'll also make them dashed to indicate that they are not part of the graph, but just in there as a guide. Okay, so you can see how these purple points here are trapped in between, right? These two asymptotes here, these purple points that are on the cosecant are trapped in between there as well. All right, and so that's basically how the graph of the cosecant is going to work, right? And you would draw over here at 3 pi, you're going to have another asymptote because that's where the sine crosses, and then you're going to have another branch up here that just comes down and touches the cosecant, or the cosecant, where it touches the sine function at these peaks and down in these valleys as well. All right, and so once you know what the sine function looks like, again, pretty easy to figure out what the cosecant function looks like. I'm going to go ahead and graph the cosecant. And let's make that purple. All right, and so you can see what that graph looks like if you connect the dots. Okay, again, if you're still confused about where these points came from, then I recommend going back and looking at the secant video where I worked out for the secant and cosine exactly, how those points would come about. Okay, so now looking at the properties of the cosecant, the first one is the domain, and the domain of the cosecant function is the set of all real numbers where x is not equal to k times pi. K is an integer. So if that's confusing to you, then go back and watch the very first video that I did for the tangent, where I explained exactly, what this notation means. It's really important that you understand that, right? But basically for each whole number integer, right, that's the whole number is 0, and the negative of the whole numbers, when you when you plug in any of those, any integer in for k, you're going to get a point where that's not in the domain. So that would be like 0 pi, which is just 0, 1 pi, right? 2 pi, 3 pi, and so on and so forth. Going the other direction, minus pi, minus 2 pi, and so on and so forth. So those are going to be points that are not in the domain. So if you try to take the cosecant of 2 pi, right, it's going to give you undefined or an error on your calculator. Those are also places where the graph of the cosecant is going to have a vertical asymptote, right? So the graph is going to get closer and closer to this line, these vertical asymptotes on either side of them. Okay, so you can see how these kind of U-shaped, although they're not exactly U-shaped, but they get closer and closer to these lines the farther up it goes. Okay, if you zoom out like that. All right, so that's where the vertical asymptotes are. Remember, the domain is the set of all real number inputs that lead to valid real number outputs. Okay. And then the range is the set of all possible outputs, right, for numbers in the domain. So again, what this is saying, that the range is minus infinity to minus 1, union 1 to infinity. This is saying, hey, if I plug a number into the cosecant function, the output, the number that I get out, has got to be -1 or less, or 1 or bigger. And you can just see that by just messing around, plugging in some numbers in here, right? You can see that, oops, that's not going to work. The numbers that I plug in are all either going to be bigger than 1 or smaller than -1. You're not going to get any numbers as an output that are in between 1 and -1. And again, the best way to see that graphically is if you look, oops, I don't want to turn the cosecant off. If you look at these horizontal lines, y equals 1, y equals -1, you can see that there are no points on the graph in between these two lines. All the points on the cosecant graph are either above this line or below this line. So what that means is that there cannot be any output value that is in between less than 1 and greater than or equal to -1. They all have to be either above 1 or below -1. All right, and then lastly, about the period of the cosecant function. The period of the cosecant function is 2 pi. So recapping all of those for cosine, sine, secant, cosecant, their period, the period of those trigonometric functions is 2 pi for all of them. And for tangent and cotangent, the period is pi. And you can see, right, if we just looked at that fundamental period of the sine, right, from 0 to 2 pi, looks like this. You can see that that you have a branch of the secant, cosecant above, and one branch below. And then remember, the cosecant's really tied to the sine function. So as sine repeats, so does the cosecant, and it takes from 0 to 2 pi for it to repeat. So 2 pi units, rather, for it to repeat from wherever you're starting. All right, and so that is it for the cosecant.